morning. Welcome everybody to another seminar. Today we have Chris North from Virginia Tech. I've actually known Chris's work for a long time. I do a lot of work in large displays, but I do a lot of the development of the hardware and the software. So Chris actually does a lot of the user studies of actually people doing research and analyses in front of them. So it's been a weird kind of relationship where Chris does all the research and I cite all Chris's research about how wonderful the tools are, and then I use that as reasons to build new tools, which then Chris does research on. It's sort of a symbiotic relationship. And one day, one of my postdocs was at a conference and he was talking to Chris, and Chris has expressed some interest in spending some time here in Hawaii, sabbatical. And so here he is. He's going to be here till May, so you have an opportunity to actually engage with him more. I'm sure he'll talk about some really cool and awesome things that he's doing in Virginia. In particular, he's also part of a data science institute, and it'll be really interesting to see how their spin on this whole concept is versus what we're trying to do. So with that, take it away, Chris.
Awesome. Yeah, thanks for the intro, Jason. Yeah, super excited to be here. As Jason said, I've got the spring semester on sabbatical, and so what better place to spend it than in Hawaii and with Jason and with you all. So pretty cool. I'm excited to be able to put the logo on my slide there. It's awesome. So I want to give kind of a big picture overview of lots of things we've been doing lately. But first of all, just the fun of sabbatical, right? So this is indoor fun and outdoor fun, right? All in one. That's what's great about Hawaii. So this is my daughter here up on Pali Notches. We hiked up there last weekend. So that's a pretty crazy hike. That was lots of fun. One of those things where if you take one wrong step, you instantly die, right? So that's all part of the fun of being here on sabbatical. So yeah, I just want to give you kind of a big picture, sort of high-level overview of lots of things we've been doing at Virginia Tech. And we can always zoom in on more details later if you like, if something piques your interest. I want to talk about a few things. One is I'm going to talk about just some of the educational data science agendas we've been working on at VT. As I understand, you're working on similar agendas, and so we might have some war stories to share. And then I'll talk about just some of the research we've been doing on big displays and interactive analytics and things like that. So with that, yeah, just a little bit about data science education at VT. This is just kind of a big list of everything from simple workshops all the way up to PhDs that you can do in data science at VT. And I think I'll just talk about a couple of these things. One is the major that we've developed, and then also the minor at the undergraduate level. And just to give you a little feel for those programs that we've developed, it was a lot of work putting these programs together, and maybe this is something that'll benefit y'all as you're working on putting programs together as well. This is actually the curriculum model of what we call the CMDA major, Computational Modeling and Data Analytics. So it's a new major that we created at Virginia Tech about 4 years ago, I think. And it was really the result of 3 departments coming together and saying, hey, we got to have something like data science at VT. So it was the computer science department, the statistics department, and the math department came together to build this major. And so it's kind of a new thing. It's a new major that's shared between these 3 departments at Virginia Tech. So that was kind of a new thing for VT to take on, is this idea of a shared major between departments. And so it's kind of run then by sort of an independent entity that's sort of under the purview of those three departments. Together, the curriculum looks kind of like this. The students come in with some math over here and some basic, intro computer science over here, and then they go through what we call the integrated quantitative science, which puts together a lot of math and statistics all into one instead of kind of stovepiped math and statistics. It's all integrated together, and this sequence of courses here. And then they come out and they do some visual analytics and some mathematical modeling, and then they finish up with this capstone here. So that's kind of the rough outline of the curriculum. Just a couple of things that I thought were kind of neat about what we put together here. One is that we've created this sort of alternate path to get into the major, because what we have found is, at least in getting started up, and even now that we've been going for 4 years, we get a lot of students coming in from like math and stats and CS who say, oh, well, I started in one of those majors, but I'd like to switch over to CMDA. And so this enables them to take the courses they may have already taken in math and stat and then pipeline in to the CMDA curriculum. So this is kind of an alternate to these new courses that we developed for CMDA. So it's kind of then two paths for ways to kind of students to come into the major. And we found that really helpful in sort of bootstrapping the major and getting it going with existing students in these majors. Trying to think of some other things. Oh, yeah, one other thing we've created is the idea of domain science tracks that go alongside the CMDA major. So you can take the CMDA with a physics option. And there's a couple other of those. There's a biology option, and I think an economics option, and maybe some others. And so the idea is you do your regular CMDA curriculum, but then you do a series of courses in one of those domain sciences with the idea that then you'd be doing data science in that domain. And so it builds up some specialty there. Something else that's kind of neat in here is, let's see. Oh, yeah, my favorite course. I teach this one right here, the Data Analytics and Visualization course. That's kind of fun in that we've developed some special capabilities for that as well. We use Jupyter Notebooks for the whole course, so all the lectures and all the homeworks and all that stuff are all done through Jupyter Notebooks, which I think works out really well for the students. But in order to do that, we had to create some new capability for auto-grading notebooks, because at VT, we get pretty big classes, right? I teach usually 80 students or so in this class. And so when we do a homework, it's important to have the ability to auto-grade those things. And so we've created a plug-in to our WebCat auto-grading system at Virginia Tech that students then can submit their Jupyter Notebooks to it, and it goes through and auto-grades, and they get immediate feedback on their homeworks as they're doing it. So that's something neat that we developed for that, and it's available. We can distribute that. WebCat is used by lots of different universities, and now we've created this notebook plugin, grader plugin for it that may be useful for y'all. Let's see. Just something else that's fun in this course, we throw in some text analytics in there to help them see that, hey, data analytics is more than just spreadsheets, right? But we can get data in all kinds of different forms, like text and so on. Oh, something else that we found to be really exciting for the students is throwing a lot of data scraping in there. Students, we have found that that's like one of the key things to get students really excited about data science, is empowering them to be able to go and scrape data off the web, and suddenly this world of data becomes available to them, and then they run off and do all kinds of independent projects on their own interests based on stuff that they're able to scrape. So we found that to be really useful. One other cool thing that I think has worked out really well in the major is the capstone that's at the very end of the curriculum. And students take on all kinds of independent projects where they're working for clients in industry partners and domain scientists around the university. So, so they can sign up to work with any of those kind of customers and solve some data science problems for them. And then one thing that's neat is that somewhere during the semester, we hold this workshop where all the students in the capstone give a kind of a short tutorial on some technology that they've learned in doing their capstone. And then we open it up to the whole university so that people can come by and learn these different technologies from students who have struggled and won the war against trying to learn how to use these technologies. So that's a neat thing as well to kind of give back, right? When the students learn all this cool stuff, then they teach others about it through these workshops. So those are some things that have worked out, I think, really well in the undergrad major that we've developed that you might consider throwing into some of your own ideas. Something else that has worked well. Oh yeah, so this is just to give you an idea of the enrollment, of how that's gone. So you can see the rapid growth. And so I think all that is to say that data science is pretty popular these days. So if you build a data science major, right, they will come, and you will suddenly find yourselves with lots of students to deal with. So this is per year, right? So like over 100 and looks like about 150 students, times 4, right, in that major already. in just 4 years. So that's pretty amazing. So it's a high demand area, and so I highly encourage you to take something like that on and try it out, because you'll end up with students coming out your ears. Something else we've been developing just to kind of expand this is the idea of a minor in data science. And so we've called this data and decisions, to try to get the sort of human factors component into there as well, decision sciences. And so the idea of this is for students who are in other kinds of majors, domain sciences, hard and soft sciences, students in the humanities. This minor is designed for them so that they can start doing some data science in their own disciplines. And so it's really designed for kind of newbies, students who have never even computed before, right? And so we start out with some really introductory options here. These are kind of motivational options to get them plugged in. This course here is like, how to program if you've never programmed before, that kind of stuff. And then they go into this pair of courses, one called Data Matters, where they learn a lot of the basic data manipulation capabilities, and then Decisions Matter, where they learn a lot of the sort of decision sciences concepts and decision trees and things like that. And then they go into this third level where they go back into their major and they start plugging those ideas and applying the data science in their own curriculum through kind of more advanced classes in their own majors. And then that then feeds into some kind of outreach where they get plugged into internships and other kinds of things, capstones and whatnot. So that's kind of the 4-level framework we've developed for the minor. And the idea is they do one course here, they do both of these, they pick one here and one here. Right? So it's kind of a lightweight series of like 5 things that they would do. And so that we're in the process of developing now. We're running the first instances of these courses just last fall. And so we have yet to kind of see how that plays out and what the bar charts look like as that grows. So those are some of the exciting things that are going on in the area of data science education at BT. Any thoughts about that? How that might be helpful for what y'all are doing here?
Nice.
How far along are y'all developing data science education here in Hawaii?
We have many courses that are not coordinated like that.
Yeah. Okay. So the key is to put together,
The tree, but no tree.
Got to build the whole graph structure, yeah.
And I like the alternate entry pathways, because
Yeah.
we just had an admissions meeting for computer science, and we get these applications from all these different fields. It's like, okay, we can't just have one set of requirements and what's their path going to be. And so it's nice to see alternate entry paths, and I like to see the way you and have a couple cores and then connect them to their discipline.
Yeah. That turned out to be more important than we thought it would be. We thought that, hey, when we start the major, we want to draw from these existing students and sort of bootstrap the major. But then what we have found is that it's also been important in the ongoing aspects of the major, because there's just constantly students that want to switch, and they don't want to have to go back to the beginning and take all this math that they've already taken already, right? And so it's been really useful to have those two paths in.
You make a grad student take undergrad courses.
Yeah.
Does they need a background, or does that just slow them down?
And in fact, back here, we're doing something similar now in the computing as well. So what we have found is that the sort of standard Java intro sequence that we have in computer science didn't fit so well, actually, with then students going in and doing data science. And so that it felt kind of disconnected. And so what we're building now is an alternate path here that's Python-based. So a Python-based intro sequence in computer science that computer science students can use as well, but then if they switch into CMDA, they're all set, right? And so they can switch back and forth and they're still good to go. So that's another thing we've been working on in computer science. And so we're just teaching that the first time this semester is a Python 1 and a Python 2 to replace Java 1 and Java 2 intro sequence in computer science. Yeah, cool stuff. So yeah, it consumes a lot of time. So be prepared to chop off a section of your life to devote to it. So yeah, full professors, that kind of stuff. I would say spare the assistant professors from that stuff. But on the other hand, it's enabled us to hire a lot, right? So it's given us a lot of ammunition to go back to the administration and say, we need more professors, right? And so I think one of those slides said that we've already hired, 10 new faculty just for that program in the last 4 years. So it has been helpful in that sense because of the growth of the enrollment in the program. Okay, so switching gears over to research. So what I want to tell you about is give you a quick overview of the research we've been doing on big displays and in interactive analytics. And I'm just going to kind of bang through a bunch of stuff. So, fasten your seatbelts. What I want to talk about is what we've learned about the role of these big display spaces in visual analytics. Why do we need these big screens? And so a lot of the research we've been doing has been trying to sort of get past the hype of, isn't it cool, to, well, why is it cool, right? What is it? Are these big screens useful or not? And if so, if they are useful, how are they useful? Right? So we've really been trying to get into the evaluation of it and figure out what purpose these big display spaces serve. And I'm actually going to kind of abstract a little bit beyond, I'm going to talk about just sort of the notion of space and its role in visual analytics. And when I say visual analytics, what I really want to talk about is how do these big display spaces support this notion of human sense making? Right? And I find this to be a nice model to think about sense making. This is from Paroli and Card, and it's kind of a cognitive model of how people go through the sense making process, the different steps they take. I like to think of it this way as here's the foraging loop where you're sort of looking for information, and then here's the synthesis loop where now you're trying to put that information together to build structure, to build meaning, right? And there's this kind of tricky thing called dual search between the two of, at the same time I'm trying to find evidence for my hypotheses and find hypotheses for my evidence, right? And it's sort of complicated, gnarly cognitive problem. And so that's what we want to be able to do, and that's what we want to be able to use these big displays to do. Just a little bit of, our equipment isn't as impressive as Jason's, but we've experimented with a few different displays over the years. This is the biggest one we ever built, was a 100 megapixel display. We have found our favorite one to be this one. This is more of a personal workspace. It's a 32 megapixel workspace. It kind of has a curved shape to it, and you kind of sit inside, and it's designed for 1 or 2 people to hang out in there and get work done. So in terms of the roles of space, I want to talk about sort of 5 roles that we've found that big display spaces play in supporting visual analytics. And the first one is really just space to visualize. And so the key concept here is that right, the fundamental limit on how much information we can display is the number of pixels, right? We can only display information based on how many pixels we have. That's our fundamental limit. And so if I have a really big display like this with lots of pixels, I can display a lot of information. And what happens then is, in order to access that information, I use this notion of physical navigation, right? So I start using my body to access the information. I step back to get the big picture, right? I step forward to kind of zoom in and see the details like this person is doing when what he's seeing right there is actually this, right? Even though we're stepped back and seeing more of an aggregated view of that, right? So physically zooming in and out, using your head to look around, right? Walking back and forth across the display. That's what we call physical navigation, right? You're navigating information, accessing it using body mechanics, right? As opposed to the idea of, hey, if I only have a small display like my laptop here, then I can't display all this information. I have to somehow navigate it through some other means, right? So I have to come up with some virtual way to navigate the information. Since I can't display it all at once, that means I have to maybe zoom out and zoom in using some sort of keyboard mouse technique, or pan and zoom, scroll bars, all that kind of stuff, right? And so that's the fundamental trade-off. With the big display, I have the opportunity to physically navigate, versus on smaller displays, I'm forced into virtual navigation. Does that make sense? 2 ways to navigate the information. And so we've tested all that kind of stuff. We've evaluated this thing every way you can think of. Here's just an example of some of those kinds of results, right? As we make the screen bigger and bigger so that we can display more of the information and do more physical navigation versus making the screen smaller, forcing more virtual navigation. When we make the screen bigger, our human performance time in performing various visualization tasks goes down. In other words, gets faster. Right? So people were faster at physically navigating in order to answer questions than virtually navigating. Does that make sense? Yeah.
What kind of questions?
Yeah, so all kinds of questions. Some of these are simple questions like, yeah, so here's the biggest bar chart you've ever seen, right? Like gazillions of little bars on this screen over here. Questions like, well, find the largest value, right? That would be a really simple one, right? Or things like, finding certain kinds of patterns, right? Yeah, solving various sort of data finding tasks like that, right? And yeah, so a couple of key concepts. The idea of physically navigating, physically zooming in and out, physically zooming panning side to side and so on. And what we saw then is not only faster performance times, but also things like better strategies, right? Hey, if I want to find the maximum value, maybe I should look in some of these bright clusters, right? That's probably where I'm going to go find the highest white bars, right? Something else you got to think about is when designing visualizations to support this kind of physical navigation, you got to sort of think about, well, how do you design the visualization, right? Because not all kinds of visual encodings will support good visual aggregation. If I physically zoom out with some visualizations, I might not see anything at all. It might just sort of disappear into the background, right? So I like to think about, well, how am I encoding my information in order to support this physical zooming in and zooming out? And so we've done experiments on that to figure out what kind of encodings work best. So here's an example of one that works pretty well using these white bars on a blue background, right? Then we get this kind of visual aggregation where you can see where where there's a lot of large values and a lot of small values and so on. As one example of that. I also get the question often of, well, what kind of data is good for large displays, right? So beyond just, yeah, I got a lot of data, so I need a bigger screen. And I think to me, right, really the key idea here is the concept of multiscale data. A good example of it, in fact, I think the best example, an ideal example, is text analytics. So in text analytics, you've got sort of two distinct scales in the data. You've got individual documents and the structure within a document. And then you've got a collection of documents and the structure of the collection of documents. And you want to be able to see relationships across all of those scales, right? So for example, you want to be able to see something from within a document up to the higher level of scale, connecting across to some other document, and then connecting to some structure within that document, going across two discrete levels of scale, doing those kinds of relationships. I think text analytics is like a really good example of things that would be ideal on a big display type of situation. We have this multi-scale. That's the idea of one role of space is enabling us to visualize these big and multi-scale data sets. And using physical navigation that's more efficient. Well, a little teaser there is the background of that idea is this notion of embodied interaction. The idea that when I'm navigating these big display spaces, let's go back to our big bar chart here. Humans are designed such that our perceptual system, our body mechanics, our muscular system, our cognition is all tied together and tightly intertwined. And so when I want to say something like, hey, if I look at this data point and then I go over here and I look at this data point, because I've physically navigated over there, because my peripheral vision is keeping everything all connected together, I get a really good understanding of the spatial relationship in that data set. Whereas if I'm using some virtual navigation technique, I'm going to have much less of an understanding of those spatial relationships. I won't have taken advantage of all those capabilities. This notion of embodied interaction. an explanation for why this physical navigation is likely to be more efficient. Extracting this spatial relation. Okay, a second role I want to talk about is space to interact. Right? So the space enables us to interact in a multi-scale and multi-object fashion. And so it kind of scales up our interaction. I'm going to show a video here if I can. So here's an example of where the interaction is physical navigation aware. So she's holding a wand and she's using that to do kind of raycast, homecast interaction with data points on a screen. And the idea there is that when she steps back and she's visualizing the big scale, she's also interacting at the big scale. She's moving big clusters of things around. Right? Then when she's interested in the details, she kind of steps forward and says, I'm interested in that individual data point. She goes up and grabs that with them. So just by physically navigating, she's also controlling her scale of interaction. And so, our studies show that that kind of capability then also amplifies our interactive capability in the sense of, hey, now I don't have to do things like switching modes or controlling, hey, what scale do I want to interact with? And all that. It's just automatically tied into how the user is physically navigating the space. So that kind of gets at this idea that we've explored a bit of this notion of we don't really have a good name for it, but we call it like anyway interaction. Right? It's like getting interactions that you're doing anyway, stuff you would do even if you weren't interacting with the system, and you're kind of taking advantage of those interactions and using them in a sense for free to do useful stuff. Right? The idea of stepping forward and backward, you're doing that anyway. Hey, well, let's take advantage of that and learn from it and use it to do other useful stuff, like in this case, control, how big a chunk of data you're interacting. Let's see. Yeah, just some other examples of that. I think I'll blow past it. Our third role of space, we like to call space to think. So we're talking about space to visualize. I was really talking about perception, physical motor skills, and things like that. When we're talking about space to think, we're talking about more the cognitive layer. And so what we have found here is a couple of key ideas. So what you see here, this person is doing a text analytics scenario. So he's looking at a bunch of textual documents and he's trying to figure out some hypothesis about what's going on across this set of documents. In this case, it's an intelligence analysis type of scenario. If you're familiar with the BAS challenges, I think it's one of those types of problems where each of these documents is like an intelligence report of maybe some observation of some bad guys doing some stuff in the field. And then the job of the analyst is to figure out, well, what are the bad guys planning, right? What's going to happen? Or the terrorist attack might happen that we should work to prevent. Kind of the scenario of the data set. And so in running analysts through these kinds of scenarios and observing how they use the displacement, what we see, actually, cool, I have a video. What we see is something like this. I'm going to give you a high-speed playback of one analyst doing an analysis of a textual data set. And it's purely a manual type of thing, right? They're just opening up these documents, reading them, organizing them, trying to make sense out of it. And what you see the analyst doing is creating structure. So they're organizing the information on the screen, using the space to externalize the structure that they're learning, right? Their own mental model of the space. So they're finding things like, oh, there seems to be a cluster here. These documents are all about, maybe some particular guy or what he might be up to. And these documents are about some other guy and what he's up to. And maybe documents that are in between or where those two guys are working together to plan something like that. You see kind of some lines here showing various relationships, co-occurrence relationships, and things like that. So there's some visualization capability. And you can kind of see over the course of an hour or so, the analyst has done a lot of structure building up to the space, and by the end, they've created a kind of full story of their hypothesis about what the bad guys are planning. So at the end, we would ask them, okay, so what's your hypothesis? And they would then use the space to kind of walk through and tell us the story of what they think is going to happen. And here's all the evidence for it. And so we think that this guy's going to work with this guy to blow up this building, you know, on that day, something like that. And you can see that process. You can see it was incremental, right? It built up over time. There were a lot of small changes. Occasionally, there were some big changes where they made some big reorganizations, but a lot of it was like little adjustments, little tweaks here and there. We like to call that process incremental formalism. It's a phrase from Frank Shipman talking about the idea of how people sort of gradually learn an idea or gradually create structure. And the neat thing about this is we're seeing the analyst do that. Right? We're visually seeing them create structure in it. And so the role then that the space plays in supporting the thinking process, the cognition, is one, the notion of external memory. That by putting all this stuff into the space, it helps the analyst remember what they've seen and find previous information in order to make connections and all that. Secondly, it provides a kind of semantic layer where now as they organize things, they're essentially labeling the data. Right? They're saying, hey, this is a cluster. They're giving all that annotation right in the display. There's also some other kinds of things they're doing, like creating little sticky notes, highlighting things that are important data documents, doing searches, all that. And what we see, just to maybe give one example of one kind of result here. So we've tested this idea of this space to think in a physical navigation type of setup, right? A big display, and now just like we saw in the video, somebody organizing on a big screen, but then also in a virtual navigation. Now you've got a small screen. You still have the same big virtual space. Now you're having to navigate that by panning and zooming. And it turns out it makes all the difference in the world, whether you have a big screen or a small screen, what your behavior is when you do that. So I'm going to explain this real quick. So this is a time series going this way. The vertical axis is which documents they were looking at that point in time. So what do you see here? In the physical navigation case, big display, analyst is organizing. They're going through and reading all the documents, kind of one at a time as they create structure. But what are they doing as they read each document? They're going back and referencing, visually referencing all those other documents. This is like eye tracking. And so as they read each one, oh yeah, that connects to these other things, right? So they're building up this rich space. And they're building spaces that look like this, same thing. Whereas, when you look at the virtual navigation case, same time series, right? Same going through all the documents and reading them all. But what you don't see is going back and looking at all the other documents and making those comparisons and connections. They tried to do it at first. They tried to zoom and pan around the space in order to keep track of all this stuff, but they quickly gave up and just read through the documents. Okay? And then at the end, they try to do some structuring in a much less so way. And then, I don't have those pictures, probably because they were so boring, because usually they were just a pile of documents up in the corner. They didn't end up really using the space at all. They just went back and sort of manually looked at a few of the documents that they just the ones they could remember. Right? So with the big screen, much richer spaces, right? Much more connections made, right? Whereas with the small screen, with the virtual navigation, much simpler kinds of analyses. Does that make sense? Yeah.
Could you also interpret this as distractions? Like on the top, you have many more distractions when you're switching tasks and stuff. Or is it?
Yeah, I mean, but I think we found it to be useful, right? I mean,
they've already looked at it and they're going back to them.
Right, they're going back and re-referencing them, right? And so it's enabling them to make the connections, right?
It's not like a new kitten
So,
showed up or something.
yeah, so in that sense, it's a useful distraction, right? They were making new connections that these folks didn't make, right? Yeah, actually another interesting effect there is the red stuff. The red is when they were taking notes and things. So notice that in the physical navigation, much less reliance on having to take notes, right? The space served as their notes, right? Whereas down here, these folks, right, they had to do more, hey, I got to write this down so I can remember it, you know, that kind of stuff, right? Yeah.
Did you ever try making a graph out of each of those trajectories, making an edge if when they go from one page to another and look at the spectral properties of the two graphs?
Yeah, that's interesting. So I think
you'll get a big spectral gap on the top one and a little one on the bottom.
okay, you're saying like spatialize the graph like this.
No, just make an edge between two documents.
Oh, okay.
If they go in sequence, reading one to the next.
Weighted
Their
edge.
eyeballs.
Yeah. Every time they,
Yeah.
every time their eyes move from one document to another,
Make an edge between
that's an
two
edge.
documents. Make
Okay,
a
that's
graph.
interesting.
And then do
Fascinating.
the documents cluster in a way in those transitions that it's similar to the way they clustered them physically in the space.
Yeah, okay. I mean, I guess you could kind of see that here. I mean, this is, in a way, this is kind of an adjacency matrix. Not exactly the way you're describing, but it is a little bit like
they
that.
looked at something down there that
Yeah.
caused them to go back and look at a whole lot of other things. So there's,
Yeah.
there's something special
Like
about
some of these documents, they said, oh, yeah, I'm not going to
yeah.
deal with that. Maybe that's a junk document, right? But hey, this one's interesting. I'm going to go compare that to lots of other things. This could maybe it could be a really critical document.
Meta document or something.
So that's really interesting. Then we could do analysis of the analysis, is what you're saying, and then say, oh, this must be a critical document. Let's mark it as important or something like that. Upweight it, bump it up. Nice, I like that. Yeah, very good.
Are the two pictures from the same people? Were the same people doing for those experiments? Because I imagine there is a big variation. Like if,
Yeah.
like the kids that are playing video games, they do much better, right? And having a great sense of the
That's right,
environment that they do.
Boy, you're going to stretch my memory here as to whether this was a between or within subjects experiment. I'm pretty sure this was a between subjects experiment, so we had a whole bunch of different participants in two different groups. But yeah, but variance is high in these kinds of, anytime you're doing this cognitively intensive stuff, variance is really high. Yeah. Okay, I'm trying to keep moving here. Our fourth space, role of space as space to collaborate. And this is, I think, where Jason's team really excels, right? With the Sage software is definitely one of the key pieces of software in enabling collaboration in big spaces. Here's just an example of, okay, so if we put two people in this space, and what we had been talking about so far was one person doing this analysis in the space, but what if we throw more people in there? Well, it turns out we see all the same effects. We see exactly the same stuff. But it turns out to be even more important than it was before, because now it's enabling this shared mental model, right? And so now later when we split the two people up and ask them each what the hypothesis is, if they had this shared space like this, they have a much more cohesive model. You can compare them and see that they line up very well. So the space really served as a shared space to think, as opposed to just an individual space to think. So it serves a good purpose in that sense as well. Also, all the other effects of physical navigation, you see neat things like, hey, they can work together and focus on separate things, but then once in a while they can say, hey, let's both focus on this, and use physical navigation to have multi-foci or shared foci. We see all kinds of interesting collaborative interactions, sometimes things like handoffs where, hey, I read this and you should look at this and put it over there. Here was a particularly interesting case where these two participants formed a kind of multiscale relationship where this guy was kind of like the detail worker, and he took control of the controls and was sort of the forager, like finding the information. And then this guy was kind of like the commander. He was stepping back, seeing the big picture, saying, oh, yeah, that should go over here, and that should go over there, right? And so they took this kind of multi-scale role in the sense-making process, which was another kind of neat way that these spaces can enable different kinds of collaborative interactions to develop. Pretty cool stuff. And I guess the fifth role of space is the notion of space for analytics. Now, this is the stuff we've been working on most recently, and the stuff I'm most excited about these days. The idea here is that, okay, so we already saw in Space to Think that we can actually observe the cognitive process happening, right? We can see how they're organizing things and so on. Well, hey, if we as experimenters can observe it happening, doesn't that mean we can create algorithms that observe it happening and make use of that information to do useful stuff, like you were hinting, right, of analysis, right? So yeah, we can do that. This is an example of one of the systems that we've built to do that. This is called StarSpire. The whole idea here is that as the analyst is doing this space to think, we've got some machine learning algorithms under the hood that are learning from the user, and learning how the user is organizing and what's important to the user, learning from how the user organizes things on the screen, learning from the user highlighting important information, learning from the user doing searches, learning from the user writing in the margins. They can type post-it notes and stuff like that on these documents. Learning from all that stuff and then using that to do two things. One, using it to go out to the bigger database of information and forge out relevant information onto the screen. And then secondly, organizing that information on the screen according to how the user is organizing it. Right? So here's an example where the user recognizes some connection here, and so the user drags this over here to kind of build a cluster. And the system recognizes that and says, oh, right, you're building a cluster there. Well, then here's some other relevant documents that I'm going to bring forward and put them into that cluster that you might also want to read, right? Because that'll be important if you're interested in that cluster, right? And oh, by the way, this other document that was over here, also really relevant to that cluster. I'll just slide that over for you there to let you know that you probably want to read that one too, right? So all this kind of dynamics is happening in the background as the user's organizing the screen. And so then it becomes a kind of collaborative process between the analyst and the algorithm to do this space to think, to organize the to create structure, right, on the screen. We like to call this process semantic interaction. We call it that because the idea is that these interactions, these anyway interactions, like I was talking about before, I'm going to highlight stuff anyway, I'm going to do searches and take sticky notes anyway. I can take advantage of those interactions that carry semantic meaning and actually learn some of those semantics from the user and then do useful stuff with it. So that's why we decided to call it that. So our kind of big hypothesis here is that the space of these large displays serves a couple of purposes. One, it can be kind of a common ground, right, between analyst and algorithm. People think spatially. Algorithms can compute spatially, right? So this can serve as a common ground for the two of us to talk together, right? Also, this idea of space as a context for algorithm input and output. So in other words, so as an analyst, I don't want to have to control these algorithms, right? Under the hood, there's a bag of words learning model here that's learning what words are important and what words aren't, right? I don't want to have a knob on every word in the English language that I have to turn, right? Maybe a few of them I'll turn, right? But there's a lot of words in there I wouldn't even think of turning, right? So that's probably not the right way to interact. But instead, I can just do this contextual interaction where I say, hey, I think these two things are related in the kind of problem I'm dealing with. Well, then I can mine out what those relationships are and upweight the appropriate words that are important in forming that cluster, right? Same with the output. I wonder if I have a picture of that. Yeah, here's an example of contextual output. As the model then learns which words are important and which words aren't, well, guess what? It can kind of reveal what it's learned to the user by highlighting those words in the actual text documents that the analyst is working on. So notice some of these highlights are a little dim, indicating, well, maybe that's important. Some of these are a little darker, indicating, hey, this one's really important. Whatever you're doing, you're honing in on that, right? And so that then gives the analyst some hints about, well, which part of these documents should I read? Which parts might be most useful to read, right? And so the idea of making my input to the algorithm and the output from the algorithm all within this space to think that I'm operating on, so I don't have to transition out to some other kind of control panel and manipulate some other kind of parameters that I don't know what they mean. Here's just an example of that happening where the user, starts to organize things, and there's some clustering going on and labeling and all that kind of stuff. That's one example of some kinds of algorithms we could use to help people. And it's kind of neat. So what we found in our studies is this notion of, remember I was talking about incremental formalism, watching the user sort of figure the problem out. We can kind of show a graph then of the model also learning over time, and we can kind of show how they go together, and that there's some correspondence between the human learning and the algorithm learning, which I think is a really nice connection that we should study more about. Another neat thing that we've seen from the studies is this notion of high level versus low level in terms of how the humans and algorithms relate. At the end of the study, when we asked the analysts, well, what did you find in here? What do you think was important? And they list out, the things they thought were most important. And then we look in the model and we see, well, what did it upweight? What did it think was most important? And we compare the two. We find a congruence in the sense that they both thought similar things were important. But what was neat was the analyst was expressing those things in higher level terms. Like, I think there's an attack in the Caribbean coming through some tourist ships, right? Whereas the algorithm would have words like the specific name of one of those tourist ships, right? A specific address in the Caribbean where the weapons were coming from, and all those kinds of things, right? And so they were similar, but at different levels of abstraction, right? So I think that's kind of a neat way to think about human AI interaction, as the human sort of providing this sort of high-level abstraction, and the algorithms helping kind of fill in the details of those high-level intuitions. Right? I think that was kind of a neat result, a really nice outcome of this kind of collaborative human AI interaction. So that brings me to a kind of a bigger pitch I'm going to make as I kind of wrap up here, getting more into the interactive AI stuff. You've heard of the black box problem, right? The idea that, well, these machine learning algorithms are kind of opaque. It's hard for people to understand what's going on in there and what the results mean. And so we have this notion of explainable AI to help people understand what's going on in there. And I think that's great and that's important. But I guess the claim I want to make is that that's really the easy part. That's the easy half the problem. I think the much harder half the problem is like this, that from the perspective of the machine learning algorithm, the human cognition is also a black box, right? And that we actually are trying to get these two black boxes to talk to each other. That's the hard problem, right? And so I like to call this explainable CI, right? Explainable cognitive intelligence, right? How do you explain it to the machine learning algorithm, right? And so to deal with that kind of two-way problem, I think that's where this notion of semantic interaction is really important, right? That using space to think, we can observe, we can get a window into the cognition. We can use that then through contextual input in the space to think, right? To feed in to those algorithms in a way that's usable, right? And then we can take the outputs of those and feed that back into the space to think in order to explain those results to the human in a way that's understandable back in their space to think, and all those good principles from semantic interaction. So I think this is one way we can attack this two black box problem. Maybe another little bit here. Some things that I think are really hard about this two black boxes stuff is that, especially when we have multiple algorithms, we've got many parameters to manipulate. The person doesn't know the meaning of those parameters. The parameters are typically lower level than at the level at which the analyst is thinking. I'm thinking of documents and concepts, right? The algorithms want feedback on words. I don't know about words. I'm thinking about these high-level concepts. The issue of premature formality, a simple example I like to use here is k-means. You can't run k-means unless you first give it k, right? I'm not ready to give it k. I can't decide how many clusters I want, right? I haven't decided yet. I'm still in the early phases. I don't know how many clusters are in here. right? So it's asking me to formalize, right, too quickly, right? All those kinds of things. So those are some of the usability problems that we encounter in this two black box problem that semantic interaction is helping to solve. I'm going to try to show one quick demo here just so you can see something actually working to give you an idea here. Get my goofy reminders off. So this is a tool we built called Andromeda. It's a pretty simple example, but I think it really demonstrates some neat ideas. What we're looking at here is some survey data I took in one of my classes. So these are all students in my class. Right? These are all names of students. These are the questions I asked them on the survey. So things like how many publications do you have? How much do you like camping on a 0 to 100 scale? Right? All this kind of goofy questions, just fun stuff. So it's a multi-dimensional data set with maybe 30 dimensions and maybe 30 observations, right? So how can we explore this multi-dimensional data set? So sure, we can project it down. In this case, we're using a multi-dimensional scaling algorithm to project the high-dimensional data down to 2D. And the idea there is that the pairwise distances is attempting to be preserved in the from the high-dimensional space, right? So notice that I'm an outlier. I'm very different from all my students in the way that I answered the questions on the survey. Notice some trends here, like these are a lot of sort of domestic-looking names, lack of a better way to say that. These are a lot of international-looking names up here, so maybe there's some effect there that these students are clustering like that. I'm not sure. But, you know, I only get this limited sense of the data because I'm only seeing it in 2 dimensions. So I want to be able to explore a little more. And just to give you an idea here of doing that, one way to do that is I can manipulate the dimensions, right? So I can say, well, you know, what about this notion of distance born? That question is how far from Blacksburg, which is where Virginia Tech is, were you born? And so I can kind of test my hypothesis about domestic versus international students over here by saying, let's put more weight on distance born. So I'm dragging that to the right. I'm saying put more weight on that in the distance function that's determining these distances. And sure enough, those clusters kind of separated out, right? So that suggests that idea of sort of domestic versus international was kind of an effect, an important effect there in the data, right? So that's kind of neat, right? But the really fun thing is if I turn it the other way around, I can ask questions in the space to think sense, right? I can say, well, why am I this outlier? What would make me be like my students, right? So I can ask a question like that and say, well, hey, let's just put me over here in the cluster, right? And say, I want to build a cluster. What would make me be like those students? And Mo, he's a international kind of guy. I'm going to drag him up here with these students, right? And then I can say, hey, give me, you know, learn from that, right? And find a projection where that is the case, right? And I can kind of replay that to see how that turned out. And sure enough, I'm over here in this cluster of students. And let me just sort that for you so we can see that, yeah, so phone minutes turns out to be the key thing, right? So these people over here in this cluster that I'm in are all people that don't like to talk on the phone very much, right? And maybe that says something about the international students calling home a lot, right? You know, and because the people that don't talk on the phone are the ones that are born nearby, right? Does that make sense? So now I can start to explore from this other perspective of, hey, I have some domain knowledge about these data points. Let me create the space that I think, and then you tell me what you mine out of the data from that. So we took this, otherwise unsupervised projection algorithm and turned it into a kind of a supervised machine learning projection that could take the feedback from my kind of labeling the space like that. So that's one example of semantic interaction in the small space. I guess let me just finish up by saying, hey, there's cool things I want to do in Hawaii. One is I want to collaborate with you all on big displays for data science. Wouldn't it be cool to see how tools like Sage can impact data scientists who are doing things like creating Jupyter notebooks that now can be not just linear Jupyter notebooks, but I can spread them out across the display so I have individual cells of code and results spread across the display, and I can start to see more complex kinds of relationships between those cells, and then collaborate and all those other good things that the space affords. Also really interested in just seeing how this notion of space to think plays out in 3D spaces. So as we get AR goggles and VR goggles, does the same notions of space to think play out now when I can organize things in sort of arbitrary 3D spaces? And what's the right way to do that? Should I have some sort of displays in my 3D virtual world that I can put documents on, or should I be able to just stick things anywhere in the space in a free-form way? All those kinds of questions will come up. So those are some of the fun things I'd like to explore with you guys, and I hope we can do that. And here's just a credit to all my wonderful students that figured out all this stuff I just talked to you about today. So with that, I'll wrap up and take questions and move on.
A bunch of related thoughts. Earlier on, you're showing somebody organizing documents and drawing links between them.
Yeah.
And some of the links were long distance. And then I started thinking about, well, graph layout algorithms could reorganize it so the links are shorter, but then there's this tension between information visualization and information manipulation. The layout makes sense to a person who may not be a good communication layout. So information visualization tries to visualize data that makes it readable to people who didn't produce the visualization. Whereas collaboration interfaces, the people who produce the layout, makes more sense to them.
Yeah,
I used to study students doing layouts of evidence maps.
Right.
And their instances made a lot of sense to them because they produced it. So having put this over there had meaning for them that was harder for me as a third-party observer to see.
Yeah,
so that's a problem with an algorithm coming in and messing everything up.
Yeah.
Is then you lose the sense-making that you had in organizing the space. Right. And so I'm seeing you're trying to find the sweet spot where it doesn't move things a lot, but it makes little suggestions. So it's more of it's the incremental idea that is important, that it's more of a, you introduce the value of the computational automation without messing up the value of the user's organization. Yeah,
so there's a fun, actually, so that turns out to be a big thing you just said, and led to kind of a fork in our research at one point. How to put this shortly? But yeah, this issue of incremental updates became very important. So when we were designing the algorithms for that star spire system, where you can organize the documents and the system kind of helps you, we found that a force-directed graph layout type of technique worked really well in that sense, where we could just update the weights slightly on the distances and so on, and the things would just move a little bit. So each time you did something, things would adjust just a little bit, and it would do exactly then what you were talking about, of sort of keeping your mental map without. Whereas
you want to transform. You don't want to jump.
Whereas that last system I just showed, you notice when I did the update, it completely reformed the projection, right? And so that was a very different kind of projection using multidimensional scaling, where it doesn't have that notion of sort of incremental updates. It says it gives you a whole new projection then when you update.
Though you took the action that caused the updates, so at least you're not just being presented whole cloth with a whole new thing. But yeah, that is an issue. Do you want to keep track of what moves where? Please run that slowly so I can watch the move.
Right. And so that kind of forked then into these two directions, where the star spire stuff was good for more long-term use, like where you're trying to solve some problem over many hours, right? And you're building up a space. Whereas the Andromeda system I showed at the end is more for like short-term use. Hey, I just want to explore this data set and look at like what ifs, right? So kind of different uses, if that makes sense. So that's a really good point. Different kinds of algorithms produce very different usability, right? Different scenarios.
And how they play out in the time span of the human interaction affecting the product of the human interaction. Something I've been thinking about for decades.
Indeed.
I knew Frank Shipman in the 1990s. We were funded by the same program.
Oh, okay.
Had to go to Germany to deliver our software or something like that.
Very cool. All right, are we out of time?
Actually, we are. Yeah, we're about out of time, and let's all thank Chris.